Guys, thank you so much. Really awesome to be here. Lots of really smart people, kind of intimidating. I haven't been on stage for a while, so I've been practicing this, and I hope it comes out well. So we're going to talk about heuristically detecting macOS malware. My name is Michael Sosonkin, and as Dave over there helped me point out, is I've been in the industry for a long time. I like to do reverse engineering. I like to build stuff. And I get super excited about malware, sometimes in that same order, sometimes in different order. My professional experience, I mean, that's kind of some of the logos I've selected down there. So I had some nice education, really fun institutions. I worked for a few years at Apple, basically chasing around bad guys all the time. Super fun. And since this is a volatility crowd, this is like probably one of the few crowds where I can actually like relate, because I spent several months porting a volatility framework to work against iOS core dumps. That's not something that I've ever seen done, so, and also not something that a lot of people understand. So I got pretty excited about that. I spent some time at AWS doing insider threat. That was kind of a strange, unusual experience for me. Turns out there's not a lot of insider threat interesting problems. On the other hand, it's a very difficult problem if you actually face and have to deal with insiders. So I learned a lot about the clouds there. And my most recent project, this is with my co-founder, Patrick. We are trying to increase security on macOS platforms. And one of the things you may notice as a difference between myself and Patrick, we're both awesome people, by the way. My slides are far more minimal, so there's not going to be anything flashy going on. It's just going to be like text and hopefully good speech. Okay, so a little bit about us. We formed back in January of this year, and our mission is pretty simple. We wanted to raise the bar on security, right? Because I use Mac all the time. A lot of people here I see use Mac all the time, but I feel like the security there has really been lacking, and so we wanted to find a way to raise the bar without actually like doing a lot of work. And so the way we found our approach to be is essentially to say, well, how about we just find all the people who develop things for macOS, for security specifically, and we give them tools to empower their work. This means that we spend a lot of time building detections. We spend a lot of time researching malware itself, and just generally kind of have fun with it. Okay, so a few things that I would want you to take away from this. The problem of macOS malware, it's not always clear what the scale is, because you kind of hear blogs, you hear talks, you see samples floating around, but kind of grasping what it looks like, the size of it, is something I want to show you. And also, what does the malware actually look like? I think you may end up being a little bit surprised how simple it is, but it's also quite effective at what it does. And also some tools for how do you actually detect it, what do you do when you find it, maybe some ways of actually defending against it before you get exploited. So I've not always been a Mac user, although somehow I still ended up convincing Apple to hire me. And at the time when I was interviewing with them, I actually wasn't using iPhones, so it was kind of an awkward conversation. But about half of my way through it, I became a full convert. I had everything up. I even convinced my wife to use Apple. But what ends up happening is you kind of start feeling a little bit safer, a little bit cleaner. Like things are simpler. They sometimes just work. And the reason for that is because Apple has really figured out that the malware is a problem. They no longer go with their marketing of like, hey, we don't have any malware. And they've built a ton of mitigations for it. You can read all of them in the Apple Platform Security book, which is like 500 pages worth of really cool stuff on how do they defend against things, how do they remediate against things. And some of them I selected here because I think they're particularly relevant to day-to-day malware detection, protection, mitigation, etc. So, and these are also the ones that I guess, like the most. I find them to be simple solutions to very difficult problems. First one there is Xprotect. I also have in parentheses Remediator, because XProtect is really kind of like the antivirus on your macOS. It's built by Apple, and it really hunts for a lot of well-known malware, and malware that is particularly impactful. So they don't really, it doesn't seem like they aim to actually protect against all threats. They just want to protect against the threats that are particularly difficult to eradicate. The remediator is interesting because not only will it detect, it will also remove malware from the boxes, right? So, and it'll do so quietly without telling you anything about that. So that's kind of like the AV, you know, Apple basically gave up on solutions and they said, we're going to do our own, because that's what Apple does. Notarization, that one I would say is probably my favorite solution, although I think that was launched way after I left. I had nothing to do with it. It's a solution that is particularly interesting because it gives a huge amount of insight onto the sort of the malware ecosystem for Apple itself, right? Because the way it works is if you want, as a developer, if you want to have your software run anywhere on Apple laptops or desktops, you have to tell Apple about it. You have to get it notarized. Now, notarization doesn't mean that it's secure or it's not malicious. It just means that Apple has a copy of it. And should something go wrong, they can go back to the database and go like, oh, look, we found an actor, and they wrote like 50 samples, and we can like close all of them across the globe. So that's pretty cool. They can also start looking at authorship patterns. They can look at, you know, maybe how this malware is written, who writes them, where they write them. It doesn't necessarily stop the malware itself, because you'll see certain samples are both notarized or maybe notarized, but they can bypass notarization checks. So it's not like a full solution, but it's a huge deterrence and a huge insight. Gatekeeper, that's the thing that just like keeps popping up every time you download something and says like, I'm sorry, I can't run it for you. You're gonna have to right click and open it and like really bypass everything. So it does a lot of the enforcement on your laptop, making sure that you run only good stuff. AMFI, this is, what does it stand for? Apple Mobile File Integrity. This is the thing that checks for code signing, so all samples have, or not samples, all software has to be signed by the author. This is the key that belongs to the author, not to Apple. And this kind of ties the author to the sample that they produce. And it also enforces entitlements. So on macOS platforms, essentially what it means is when you write something that requires extra privileges, you have to declare that. You say like, hey, I'm going to take screenshots, I'm going to use networking, I'm going to, you know, access certain files. Like, here's a list, sign with it. You know, if anything that goes beyond that, basically Apple is not going to allow you to run that. SIP, TCC, sort of similar. They essentially prevent access to certain directories and resources on the laptop. So if you want access to the microphone, it's going to say like, hey, something is trying to access your microphone. Everybody just clicks allow and they don't care what it means. System integrity protection has been around for a long time, but essentially it protects certain files and directories on the system so that you can't actually persist there, you can't write there, you can't corrupt the system, and you know, let's say you're actually doing an investigation on the machine, you're doing forensics work, you can rely on those files being legitimate and from Apple. So that's kind of cool. Unfortunately, that's what the size of current samples looks like. This is not number of infections. This is number of malicious samples. Courtesy of our friends at Reversing Labs, they provided the data to draw this graph. And this is essentially from January of this year. The last point there, just to note, it's extrapolated. I did not make this data up, because obviously October is not done yet. So I just kind of did average per month multiplied by number of days, average per day, a number of days. I think it'll probably land somewhere there, but maybe somebody will just dump a whole bunch of malware. And so these are particularly samples that have been identified as malicious, and there's like hundreds per day that are coming out. So except in the summer. Summer is a little bit cleaner, so just don't open your laptop until like June, I guess. So that's 45 samples a month, 4,500 samples a month. I think it's kind of a lot, particularly for the amount of work that Apple has done to mitigate against this. I think it's also a lot, particularly that Apple doesn't have as big of a marketplace for desktop laptops out there as Windows does. So I should have done a little bit more research of figuring out what the percentage points are in terms of microshare, but nonetheless, this is a lot of samples. What the size of the infection is, that's probably a different question. So we know the scale. Let's actually look at some of those things. What do they look like? So here's one. This one is called Wintail / Wintape. I will do first Wintail, then we'll get to the tape part. This sample was presented first by Taha Karim in 2008. A little aged. I know I said modern, but this is still quite representative. This was, I guess, detected by dark matter. I don't think Taha is a dark matter anymore, but it doesn't really matter for this case. This is a sample from some obscure espionage actor that really likes to target people in the government space, not in the local government space, but like in the Middle East government space, critical infrastructure and government departments. What I find interesting about this actor particularly is that they rely on spear phishing, and they also target individuals. So they don't really care if a person takes their work laptop, goes home, or takes their home laptop and goes to work. They're still going to go after them regardless of what devices they're using. The way that the infection vector worked, this was pretty cool. I think for the most part, it's actually still effective. On the other hand, Gatekeeper kind of prevents the last stage of it. So what the actor does is they send a phishing email or phishing SMS, and they say, like, please go to this link. Raise your hand if you've ever seen somebody not click a link. I don't know. It seems like everyone just really wants to infect themselves. So once you click the link, the website that it goes to will download an archive. In Safari, when you download an archive, it's automatically unarchived. To be honest, I still don't understand why this feature is there. I really don't like it, but people love it, and it works. And what happens on macOS is that all applications, they come in sort of these bundles. And a bundle is just a directory with a lot of metadata. It's structured in a certain way that the operating system expects it to be. So the binary is located in a certain location. There's metadata plist somewhere in there that describes what this application is. And one of the things that happens is once the bundle lands on the file system, the operating system just goes, oh, there's an application. Let me open it up, analyze it, figure out all the parts of it, and register it in the system. In this case, what it does is it registers a URL schema handler. In this case, what is it called? Open URL 2622007. And it says, oh, if somebody opens this URL, I am going to run this application and send this request to this application, and it's going to handle that. So this mechanism works for things like, opening a Zoom session. It's like Zoom : / oh, okay, there's your friends. You can talk to them now. And so it's useful, but I don't know why you'd want it to be as an automatic mechanism. Of course, once the application is downloaded, it's unarchived. The attacker knows that it's been registered. So what the first thing they do is they change the location of the window they're at to a URL that starts with this schema. That runs the application. And at that point, this is when the user was infected. Today, this part is going to work less well because it's going to basically send the user in pop-up hell where it'll say, like, hey, are you sure you want to run this? Are you really sure you want to run this? And if you're really sure you want to run this, follow these instructions, and maybe I won't even let you run it anyway. So hopefully they fixed that, but this flow should still work just as well. And so I tried it. It works on my machine. This one was screenshotted from 14.3 or 14.5. And what this malware does is it masquerades itself as a PowerPoint. Very clever technique by changing your icon. It will also register itself as a login item. And back in, 2018, this was infected. This view did not exist. So when something was a login item or a launch agent, you really as a user, really couldn't have a good way of seeing what it looks like or where it was registered or having kind of control over that. Today, this is visible, and that's great. You will even get a pop-up that says, hey, login item was added. I've never seen anybody take an action on that pop-up. They will just look at it. I am a tired corporate user. I'm just going to close it because I've got a presentation to go to. So thank you. So next one is WinTape. So the names are not a coincidence. They came as a package. So WinTail will actually download this thing called WinTape, and WinTape is there to do the actual collection. So one thing to note, actually I will go to that later. So once it's downloaded, once WinTape is downloaded, it will persist the same way. I don't think this malware was particularly well engineered, but it will persist the same way. It will create a login item, and it will sit there and execute every time you restart. When it runs, every 10 seconds, it will call screen capture, which is a utility provided by Apple. Really useful utility. Every 10 seconds, it will take a screenshot, exfiltrate it to this URL, and success. So okay, so this is what they look like. Both are legitimately signed. This is the team ID. It's no longer valid. Obviously, this is one of the benefits of the Apple ecosystem. They can just say, like, I'm sorry, you're an author of malware. You no longer get to publish anything. At which point, the members of the team, they re-register for a different team ID and resume exploiting their users. Pluses and minuses. I mean, I think it's still a good idea. So it's obviously now revoked by Apple, so you can't do that. Now, back in the day, notarization wasn't a thing. 2018, a little bit too early. However, there are also samples that have gotten through the notarization process. So Schleyer 2020 and 21, and Electrum Stealer, all three of these have been notarized. I think the last one actually wasn't notarized, but it found a way to bypass notarization. So it's a really cool mechanism and cool insight into malware systems, malware ecosystem, but it doesn't work every single time. Okay, so next one is also an APT. This one was published by ESET, Mark Etienne, and Anton. Back in, oh, actually I have these notes here. Back in 2022, so that's fairly recent. And it's also quite representative of what the malware looks like. So this one was a little bit more classic type of an exploit or exploit chain. There was a watering hole. It was an exploitation through a pro-democracy website in Hong Kong. Personal opinion, I don't like watering holes. It's kind of noisy, it doesn't last very long, and also like the blast radius is super wide. There's a lot of casualties going on. But this actor didn't care. They exploited using CVE in WebKit. Unfortunately, it wasn't quite confirmed as if it's the same one. I think there was just not enough information in the CVE report. But the Mark, Etienne, and Anton, they think that it was probably this one. So the way this one worked, it was kind of a classic exploit chain. So they went through the browser. It literally downloaded this binary into this location. What is it? .local software update. And then as it executes, it would persist through launch agents. This is kind of similar to the login items we saw previously. It will also steal the keychain using an exploit as well. Now, what's cool about this is that this binary is completely unsigned. It's just sitting there. It is also not quarantined. So on Apple, when you download something through a browser, from the internet, there is a quarantine flag. And this quarantine flag basically tells gatekeepers, like, hey, don't allow this thing to just execute. Do like all kinds of signature checks. Because it came through an actual zero-day exploit at the time, it was possible for that exploit chain to remove the quarantine flag and allow this thing to execute. At which point this also connects to a hard-coded IP address, port, and reaches out and uploads all the information. So I personally don't think that they expected this thing to last for a long time, but because watering holes are noisy. Next one, so this is a penultimate sample. So this one is from a cyber criminal group in Russia. They kind of didn't really try very hard. They just wrote some software and people just kind of ran it. It's genius. So they used social engineering to install it. It was not even signed. That's the cool part. Like, it was not even signed. So somebody literally just like really wanted to exploit themselves. They're like, hey, I want some ransomware. It didn't. When you actually look at the sample, like at the code itself, it looks like it was just cross-compiled. Like it was a Linux code, and there was a sample for Linux, and it was just compiled for Mac. macOS is POSIX compliant, so it just kind of ran. Everything worked fine. I don't know how many boxes they actually got, but it seems to have worked out for them very well. They did use one advanced technique, which is the anti-analysis technique using ptrace, and they said, please do not attach a debugger to me. So that one was difficult. You had to knock this one out and then eventually analyze the sample. Okay, so the last one is actually one of my more favorite ones, because this one is a supply chain attack. This is a Lazarus Group North Korean sample that was discovered because they had injected themselves into supply chain of this 3CX company. It's a telco. They provide like VoIP software or something like that. And they were able to inject in their development shop because it was a separate group. They broke in, they put in some source code, and so they were able to get in there. The Windows side was actually one of the more prevalent ones, but what's interesting is that it reached out to the same infrastructure from Mac as they did for Windows, and that was one of the ways they were able to discover. Although, to be fair, it's, if you're doing investigation on this, you're probably going to say like, well, there's a whole bunch of supply chain attacked Windows boxes. We should probably check their macOS client as well. So what they did, what this actor did, is they infected a binary called libffmpeg. So I think this is an encoding-decoding library. And what's interesting is that they actually did not even bother working on the ARM64 version. They just infected the Intel version. On Apple, it would still run because malware will get translated into ARM64. However, because the sample, the actual software package was compiled for ARM64 as well, I don't think that would actually happen. In fact, Apple would just, macOS would just run the ARM64 version. So I don't know why this happened. I have a couple of theories. One is they probably didn't have any developers that realized that this is what you had to do. And two is, well, maybe they were targeting Intel Macs because that's what their actual target was running. And so they didn't want to infect the ARM64 version. This is if they're a clever actor. I don't know if they are. And what they might have realized is that, hey, if we attack only the Intel versions, somebody will pick it up and they will not analyze the ARM64 version. They will only look at the Intel version and they'll find there's nothing wrong there. I don't know what the reality is. So this one was a supply chain attack, which means that the sample was entirely signed, it was notarized, it was entitled by 3CX, and so it sort of bypassed a lot of these things. Like there's very little ways of dealing with that. And as you know, supply chain in software is a huge problem right now. Like if you have something running on your laptop, like can you really say what's in there? Like I cannot. I don't even bother trying at this point. So this was something I wanted to say about notarization, because even though all these samples could be notarized, even though there's so much notarized software there and there's a lot of notarized malware samples, what ends up happening is that even though Apple claims that there's some kind of malicious content scanning, there's limits to that, because there's so many producers out there and you have to do it really quick because you can't produce so much friction to the development cycle. And so I think that there's only so much it can do, and so you're going to end up with a lot of a lot of malicious software being notarized. And as we saw with Windtail, Windtail by itself wasn't particularly malicious because it wasn't really doing anything. It was just sitting there, and then it would download something else. Lots of packages do that. If it's doing an update or something like that. And so it creates kind of like these multi-stage samples where the first one doesn't look malicious, second one actually does all the action. Okay. So kind of to review, I think you remember everything I said, but it's the APT. There are a couple of APT samples. There's one with a WebKit exploit that was pretty cool. There's ransomware. There's supply chain attacks. So how do we actually bring it together and actually start detecting those things? Some of the commonalities that you may notice across macOS malware, not just the ones I pointed out, but these are meant to be representative samples, is that their persistent mechanism doesn't tend to be particularly complicated. They just use the things that Apple provides, right? They use log agents, they use login items. There's a few more other ways, like they can do browser extensions or whatever. Some of them are questionably signed, notarized, not notarized, sometimes signed as ad hoc, usually signed as a legitimate user or rather developer. And we still have to kind of deal with that. A lot of samples will end up using off-the-land software. So, like curl is very common. How you can't just say like nobody can use curl. Screen capture we've seen is being used, and that's a really good way of doing useful things on the system without actually looking like you're doing anything malicious. Anything to do with networking is always useful. One of the samples was reaching out to infrastructure meant for Windows, so like we can use that to do detections as well. And what's particularly frustrating is unless you have some kind of an exploit, and a lot of times you don't, a lot of the sample really depends on the user clicking stuff. And as we've seen, they will click stuff. We already know that. They will just do that. So this is what we've built to kind of help raise that bar. So this is what the architecture looks like. Nothing too dramatic. We have a decision engine with rules. We have collectors that actually collect all the different data types. What we've done, and that part I'm particularly proud of, is we themed our collection points, collectors in different categories. So you have like networking, you have processes, you have persistent methods, etc., etc. There's like several we've written out. And as a user, you're able to essentially say like, well, I only want these certain collectors because that is my performance sort of requirements out there. I cannot listen to the networking side, so don't collect those things. And then when the data goes out to the decision engine, there's a tree evaluation, and if it reaches a point where it says like, oh, I need certain data types that are very expensive to evaluate. So if you want signatures, for example, for files or processes, you don't want to collect for all of them. You only want to collect if there's enough reasons to do so. And so the decision engine will go back and forth and say like, oh, okay, now I want like a signature check or notarization check on this particular process or this particular file. So this is a way to create something that is highly performant and still able to make those decisions. The interface is really meant for developers. So like I said, we're building an SDK. We're trying to give this to people that actually build other things like other EDRs and VMs, other different types of solutions that require to have security in them. So it's meant to be super simple, specifically so that you can have people working on it that are not security engineers, because I think that's one of the problems with building teams like that is you really want somebody writing security tools who also understand the security. Unfortunately, what ends up happening is you have a lot of really good software engineers that don't particularly understand security, and they have to be able to still write really good security controls, in this case, detections. So that's kind of what we built, but we built this stuff on top of the endpoint security framework. So at some point, Apple just decided that, look, there's all these security solutions out there. They all kind of suck. can we make something better so that it doesn't create a lot of performance problems. It maintains the user experience on the system. And this is built in parallel to XProtect, even though XProtect kind of does a lot of the features for antivirus detection. They also want to be able to support other users. So this is a C API monitoring system. It has lots of really cool events. So you can do like process executions. You can actually block processes as well if you want to decide that a process shouldn't execute. You can check for file mounts, like let's say you plug in a USB stick or something like that. Forks, signals, and a whole bunch of other things. Now to actually use this framework at large, like if you want to deploy something, you have to have a special entitlement from Apple, and Apple will actually scrutinize you to say like, well, do we really want you to build software on this? Because if somebody malicious actually had access to this framework, like that's great, that's better than having root because you have access to all kinds of stuff. So at W, they are our friends, so they know who we are. They said like, yeah, sure, you can write anything you want. It's not entirely true, but it's nice of them. And the way it works is essentially you connect to this endpoint security as a client. So you kind of say, well, I declare myself to be a client of this framework. Please allow me to receive events there. This is kind of what it looks like for allowing processes to execute using this framework. So this is a sort of a copy and paste from our code at W. The way the flow works is you call this function called ES new client. This is you're declaring yourself to be a client, and then you pass a callback function where you start receiving messages. And inside of that message, there will be a description of what type of event this is, and the audit token for which process this event belongs to. So if a user runs ransomware, you can get in here, decide whether or not you want to allow to execute it. So in our case, one of the things we do is we do a hash check. We say like, hey, this is a known sample. Don't allow it to execute no matter what happens next. Once you create your client, you don't automatically receive your events. You have to subscribe to them. And it gets a little bit complicated with the way that the framework works because Apple has this mechanism for muting and unmuting different things, in this case paths, where there will be certain default paths that are muted so that the framework doesn't flood you with events. And so what you have to do is you essentially have to unmute everything and then remute those things that you are interested in listening to. I say that muting those events that you're interested in listening to because what we do first is we invert the decision making. So anything that you mute actually becomes unmuted, and anything unmuted becomes muted. It's kind of an interesting design, but it works really, really well. Oh, and then the last thing you do is you essentially say, hey, I want to subscribe to these two events. Please send it to this client. And I think you can have something like 64 different clients on any one application. So it's kind of up to the user to manage that. There are about 152 different event types. Last time I checked, Apple adds new ones all the time, which is great. Here's just like a few of them I sampled out, which I think are kind of representative of what you get. I talked about authenticating executions for processes or allowing or disallowing file accesses. There is one for XProtect for whether or not it has detected malware or has remediated malware, which is particularly useful. There's one for launch agents. The BTM stands for Background Task Management, I believe. The last one there is kind of my favorite. I think this one is really cool, and it doesn't get a lot of attention. So this is the XPC Connect event, and if you know how macOS works, pretty much everything functions across these XPC messages as an inter-process communication mechanism. And you could have really good insight into what's happening on the system if you can say like, oh, these different agents are talking to each other, but they didn't used to before. What's going on? Why are they talking? So I think you can do a lot of anomaly detection this way. Okay, so these are the mechanisms. At W, we also built some rules. So these are This is our like rule definition language. I'm particularly proud of that one because what we do is use Python to define our rules. Super simple. You can rely on people actually knowing the language. And then what we do is compile that into a more efficient format and into a tree-like data structure for evaluation. So this one is for detecting persistent type, so for alerting us if persistent type occurs. This one here is for our network monitoring. We actually block network events to malicious endpoints. So if a sample or like an application reaches out to a C2 infrastructure for some known malware, we'll actually block that using system extensions. This one here is essentially a rule that says don't run anything unauthorized. I think that should be pretty obvious to do anyway, but in an enterprise, this is probably the thing that will capture like 99% of malware, because I think in any reasonable enterprise, you can just say, don't run anything unauthorized. I think you'll be okay without that. On a more consumer space, I think that's a little bit harder because people may want to run some unauthorized stuff, although I wouldn't recommend it. This is the last rule I'll talk about. This one is really meant to show off the more complicated version of how you can make sort of compound rules. So here, what I'm trying to do is essentially say, well, if you have an unauthorized application running on a system, don't allow it to execute curl, right? And the way it works is essentially says, evaluate something on one process namespace, and then take a key from that namespace and evaluate something on the other namespace, and then combine the decision together. So yeah, so lots of malware, lots of commonality. I think one thing you will find is that the malware on macOS isn't particularly complicated, except a few very high-end APT actors. I don't know which ones they are, but maybe they're around somewhere. And also, there are some really good tools for detecting it, and so hopefully we can write some tools to do that. Yeah, and that's basically it. If you have any questions, I'll be around, and I hope you enjoyed it.